We see an exponential decay model in a kind of an interesting little application called Newton's law of cooling. And this is a formula that tells us how to approximate the temperature of an object that starts out different than the temperature of its surroundings. And then we can look at how that slowly approaches the temperature of the surroundings. So we've got a couple of variables here. We've got T naught, that's the initial temperature of the object. T sub s, which is the temperature of the surroundings. And then, of course, T is time. And then K is a constant, a positive constant that depends on what the object is. Okay, so if the object is much easier to change temperature, then we're going to have a different K than an object that will not change temperatures easily. So this is our formula here, and it's really actually quite straightforward. It looks maybe a little more complicated than it actually is, because you just plug in all these values and then it's a very straightforward function. So let's look at an example. A cup of hot cocoa has a temperature of 210 degrees Fahrenheit and is placed in a room that has a temperature of 68 degrees Fahrenheit. After 15 minutes, the temperature of the cocoa is taken and it shows 140 degrees Fahrenheit. Find the temperature of the cocoa 20 minutes after being placed in the room. So what we need to do here is, of course, we're working with our Newton's law of cooling. We've got our temperature at time t is equal to the temperature of the surroundings plus, and then we've got our initial temperature minus temperature of the surroundings times e to the negative kt. So we can plug in everything that we do know here. Okay, what we do know is, of course, the temperature of the surroundings, which is the 68 degrees Fahrenheit. And we know the initial temperature was 210 degrees Fahrenheit. So we can go and just plug all of that in. We have our 68 plus 210 minus 68, e to the negative kt. And of course, there's one thing we don't know here, and that's k. And that's why this other information is given, that after 15 minutes, the temperature of the cocoa is 140. So let's go ahead and use that. Okay, we know that our temperature should be 140, so 140, and that's when our time is 15. So we've got 68 plus, we can go ahead and simplify this here, so 210 minus 68 is 142. So 142. E to the negative k times 15, because after 15 minutes is when we're 140 degrees. So now we can use this equation to solve for k. So if we subtract 68 from both sides, okay, then we get 140 minus 68 is 72. And then this equals 142 e to the negative 15k. And we can divide both sides by 142. So 72 over 142 equals e to the negative 15k. Then we can get rid of the e, the base, by taking the natural log. So natural log of 72 over 142 equals negative 15k. And so we can divide by negative 15 and get k. So k equals negative 1 over 15 natural log of 72 over 142. Now we know k, and we want to find the temperature of cocoa 20 minutes after being placed in the room. So now we'll just go back to our model. We could plug in k, and we can plug in 20 for t. So we've got t of 20 is equals 68 plus 142 e to the negative k, so that's 1 over 15 natural log of 72 over 142 times t, which is the 20 minutes. So this is what we need to find out. So we can go ahead and plug this into our calculator. You want to be very careful because there's a lot of stuff going on here. Okay, so use parentheses. Don't be afraid of them. 68 plus 142 e raised to the. Then we've got all that stuff. So I'm going to go. It's already in parentheses here. I've got 1 over 15. So 1 over 15. And then we're multiplying that by the natural log. So natural log, and it gives us parentheses there. 72 over 142. Close the parentheses, and then multiply that by the 20. Okay, and close parentheses. And we get 125.4. So 125.4 degrees Fahrenheit. And you just want to make sure, just ask yourself, does this answer make sense? And in this problem, we knew that after 15 minutes, we'd gotten down to 140. So another 5 minutes, taking us down to 125.4. That makes sense. For part B, how long will it take for the cocoa to reach a temperature of 90 degrees Fahrenheit? So now we just go ahead and take our model, okay, which we've got right here, and we set it equal to 90. So I've got 90 equals 68 plus 142 e to the 1 over 15 natural log of 72 over 140 t. So we can subtract 68 from both sides. We get 22 equals 142 e to the 1 over 15 natural log of 72 over 140 t. We can divide both sides by 142. So 22 over 142 equals e to the 1 over 15 natural log of 72 over 142. I somehow changed that into a 140. Let's be careful about that. That's 142. T. And now to get rid of the space, we take the natural log. So the natural log of 22 over 142 is equal to 1 over 15 natural log of 72 over 142 times t. So now I got to get rid of all of this stuff to get my t. So we can multiply by 15. So 15 times natural log of 22 over 142. And then divide by that natural log of 72 over 142. And this is t. And now we can plug that into our calculator. So we've got this nice big fraction. I'm going to go and use some parentheses here. I've got 15 and then natural log of 22 over 142. And then that's my numerator. And divide it by the natural log of 72 over 142. And enter. Oh, and there we've got a problem. Let's go find the issue here. Oh, yep. Had too many parentheses there. Closing. Delete. All right. And we get, we'll round this to the nearest tenth, 41.2. So t equals 41.2. And our time units here have been in minutes this whole time. So this is minutes. And we want to just make sure that this answer kind of makes sense in the context of the problem. So if we look at our problem, we dropped from 210 to 125.4 in 20 minutes. And we're saying after another 20 minutes, we're now dropping down to 90 degrees. And that seems to makes kind of sense to me. And then for part C, we want to sketch the graph of this function. So we can go ahead and use what we already have and use as well as some reasoning about what this function is doing. We've gotten up to about 40 minutes, and we talked about what happened at 20 minutes and at 15 minutes. So we can kind of plot those points. We know that our surrounding temperatures are 68, and we started up at, maybe I should be a little bit more careful here about my scaling. We know that the very highest, what we started at, was at 210. So I'm just going to write 200 here. Cut that in half from my 150. Okay, so 68 is actually probably right around there. So 68. So we start off at 210. So, probably right around here. And we found that we know that after 15 minutes, we were at 140. Okay, so there's 150. So after 15 minutes, about 140. And then after 20 minutes, we were at 125. That's going to be right around there, kind of right around there. And after 41.2 minutes, we were down to 90. Okay, so that's going to be maybe right around there. Okay. So we can see that we're decreasing, but it's becoming more gradual. Okay, and if you think about what's happening here, an object, this object that we've placed in a room of 68 degrees Fahrenheit, the object's not going to drop below 68 degrees Fahrenheit. And so that actually gives us a horizontal asymptote. Okay, and so then we can go and just kind of sketch the curve here, and it's got to kind of level out there. Okay, this is a very sloppy sketch, but just kind of a smooth curve that comes down, goes to those points, and levels out.